So, hello everyone, how are you all? I hope you all are fine and safe. Well, again, welcome back to Quant Coffee. I'm Aman, just welcoming you all to a new amazing video in which we're again gonna talk about the Legendre's duplication formula. Well, uh, if you are a new viewer to my channel or to my this video, so let me remind you that I have uploaded one of the proofs of this duplication formula earlier, and actually it was titled with Legendre's duplication formula, so you can just check that out if you want. But this video is gonna be slightly different, but we're just going to begin our proof with the same way that we did in that video. So yeah, actually let me tell you what's the difference between this video and that video, and why you should watch this private, like keeping in prioritize rather than that one, because that was around 32 minutes I think, and I used tricks functions, trick substitution, so that just made that video slightly messy. So but we're not gonna deal anything like that in this video. We're just going to use straightforward use substitutions, and we are good to go with our proof of this fascinating and fantastic relation. Yup, and let me tell you something. I think it's more curious that maybe I'm not sure, but I'm looking for to just bring a new video. Maybe in the next video would be on the triplication formula. So basically, that would be in the relation with gamma of 3z. But today, we're just gonna talk about the gamma of 2z, right? So I think we should begin our proof. Like, yeah, it's gonna take time, but I think not that much. Okay. So firstly, if you have watched that video of mine, so you must have noticed that I began that video with beta function. So again, as I said you that we are just going to begin our journey with beta function here. So let me tell you something about beta function, and if you want to learn about beta function, so I have uploaded an introductory part or maybe some integrals evaluation on by which, like, yeah, generalizations actually from beta function. So if you want, please check that out. And then after you will have a better understanding about beta function, right? So basically it is beta of x comma y. It is being represented with an integral from 0 to 1 of t to the x minus 1 times 1 minus t to the y minus 1 dt. So yeah, that is what it is. It's the integral representation of beta function, and in the video, like which I'm talking about, that is the introductory part of beta function. So in that video, I have proved this integral, or maybe this one, as beta of x comma y equals gamma of x times gamma of y over gamma of x plus y. So that is why I'm just requesting you to please just watch that video, and then after this come back to this video, because then you will have a better understanding of this one, the beta function. And if you don't know about it, I'm not sure that you're gonna catch all the stuffs directly, because we're just going to play around this only. But since I'm not going to talk about the trigonometric function, and then let me tell you, even here, beta of x comma y is also being represented with this integral from 0 to pi over 2 of, I think it's sine to the x minus 1 theta, and times cosine to, I'm sorry, it's 2x minus 1. Please check that out. And cosine to the 2y minus 1 theta d theta. So basically, it is when you plug t equals maybe sine theta or cosine theta, so you're gonna have this result only. So we did just played with this integral, but basically this integral is looking quite maybe sweet than that one. So that is why I'm just gonna not considering this one, but we are just going to play around with this. So yeah, I think we should begin, because I'm just keeping in mind that I have to complete this proof with less than 32 minutes, I think. Okay, let's just do that. So first step, let's talk about beta of z comma z. It means x and y both are equals with each other, and that too equals to z. So that is gonna give us, if we talk about the integral, so integral from 0 to 1, it's gonna be t to the z minus 1, it's minus, and 1 minus t to the z minus 1 dt. And basically the beta of z comma z equals gamma of z times gamma of z over gamma of z plus z. So that basically says gamma squared of z over gamma of 2z. So I just want you to keep in mind that this result, like this beta of z comma z is equal to this thing, because we are just going to use this later on, maybe in the final step. And now we're just going to talk about this integral. So I'm just going to assume that, or let's not assume, let's play with writing beta of z here. So basically it's integral from 0 to 1, t to the z minus 1, 1 minus t to the z minus 1 pt. So now let's just play around a little bit with that. So rather than just putting t equals any trig function like cosine or sine, let's just plot t equals 1 plus, let t equals 1 plus u over 2. So if you talk about the bounds, so when you plug t equals 0, so u gonna be negative 1, 0 is gonna be negative 1, and when you talk about 1, when you plug t equals 1, so that's gonna be 1 is gonna be 1 only, right? And dt is gonna be du over 2. So basically beta of z comma z comes out to be integral from negative 1 to 1. This t is gonna be replaced with that one, so 1 plus u over 2 to the z minus 1, and that's gonna be when you subtract this by 1, so that's gonna give us 1 minus u over 2 to the z minus 1 and du over 2, right? Okay, so far it's good, and it's not pretty difficult to evaluate, like till here. Next, we can think about something here, beta of z comma z. Well, we can write this as integral from negative 1 to 1 of 1 plus u to the z minus 1 over 2 to the z minus 1 times 1 minus u to the z minus 1 over 2 to the z minus 1 and du over 2. So if we combine all these three denominators with each other, so we're gonna have, when we combine all these three things, so we're gonna have 2 to the 2z minus 1, I think. Yeah, that's fine. And since it's not depending on u, so it's a constant and it will be considered as a constant, so it's just gonna come out of that integral part. So now let's talk about that here. Okay, so beta of z comma z equals 1 over 2 to the 2z minus 1, right? And then the integral from negative 1 to 1. Okay, let me talk about here slightly, a little bit here. It's 1 plus u and it's 1 minus u, and the exponents of these two terms are equal each other. It means basically they're just going to multiply to each other, and the power would be like common, right? So 1 plus u times 1 minus u, it's 1 minus u squared. So basically it's 1 minus u squared to the z minus 1 du. That's it. And now, since u square is an even function, so we can just talk about this limits. So that's gonna be beta of z comma z equals 2 over 2 to the z minus 1 integral from 0 to 1. Earlier it was from negative 1 to 1, but it's an even function. So for that case, we can consider just putting 2 in front and just integrate this from 0 to 1. So it's 1 minus u squared to the z minus 1 du. Okay, now next what? So now let's again use let u squared equals let's say that we can consider let's u squared equals y. So if we talk about du or not let's not y, actually I don't like writing y multiple times, so let's consider v. So du is gonna be 1 over 2 square root of v and dv actually. So yeah, and the limits would be same, the bounds would be same. So we can talk about beta of z comma z here. So that's gonna be 2 over 2 to the z, 2 times z minus 1 and times integral from 0 to 1, and it's 1 minus v to the z minus 1, and it's dv over 2 times the square root of v. Okay, now it's good. And now we can just cancel out this 2 with this one, and now we can consider writing this the square root of v in numerator as v to the negative 1/2. Okay, so yeah, it's good. So let's just consider that one here. So basically we are having beta of z comma z equals 1 over 2 to the 2z minus 1 and times integral from 0 to 1 of 1 minus v to the z minus 1 and v to the negative 1/2 dv. Okay, and let's just do something here again. So basically beta of z comma z can be written as 1 over 2 to the 2z minus 1 integral from 0 to 1 1 minus v to the z minus 1. Well, negative 1/2 can be written as v to the 1 minus 1, I'm sorry, it's 1 over 2 minus 1 dv. Okay, and now again, if you have watched my beta function introductory video on beta function, and if you are watching this like carefully, so now you can think of this integral a little bit here. So well, let me just talk about the beta function. So beta function of x comma y was integral from 0 to 1 e to the x 1 minus t to the, I'm sorry, it's negative 1, oh, and 1 minus t to the y minus 1 dt. So if you look closely, so we can just replace t with v because that's an index variable, so they're not gonna bother us anymore. And because it's an it's a definite integral, so they're not gonna bother us anymore. So we can just plug t with v or anything else. So basically, if we talk about, so x is 1 over 2 if we compare this, and your y is z. Isn't that amazing, guys? That's really amazing, and we are very closer to our result. Okay, that's fine. Okay, so basically what we are getting here, beta of z comma z comes out to be 1 over 2 to the 2z minus 1, right? And then we can write this as your x was, your x was 1 over 2. So we can write this as beta of 1 over 2 times, beta of 1 over 2 comma z, because this integral is representing the beta function with x being 1 over 2 and y being z. Now, well, as I told you to remember that this beta function is just gamma squared of z over gamma of 2z, and then it's a factor 2z minus 1, right? And we can write this as in terms of the beta function in terms of gamma functions. How we did that? it was gamma of 1 over 2 times gamma of z over gamma of 1 over 2 plus z. Now this it's a multiple of 2 gamma of z's, so we can just cancel out 1 with this one. And again I have talked about, I think, multiple times about the gamma of 1 over 2. It's the integral from negative infinity to positive infinity of e to the negative x squared dx, and that is the square root of pi. Well, it's not depending. This one is not depending on this integral, because that integral is the classic Gaussian integral. I just said that because these three things are equal to each other, but basically we can just use this one to find the result of that one. Okay, and if you want, again I would, maybe I have proved this this result in that old video of Legendre's duplication formula, or if you want I would just prove this down in a little bit, or let me just talk about this later on in this video only, don't worry about that. But yeah, we would need something. I would tell you what's that. So we are having gamma of z here over gamma of 2z equals 1 over 2 to the 2z minus 1 and times the square root of pi over gamma of 1 over 2 plus z. Let's just rearrange terms here, and finally we are good to go with our final result here. And I think I took less than 32 minutes, I'm not sure, let me just check that down. Oh my god, it's basically half of that time, I think. Okay, so now if we talk about if we talk about this one, so let's multiply both sides with gamma of z plus half. So it's gonna be gamma of z times gamma of z plus half, and this one is gonna cancel out with that one actually, if we are multiplying both sides with that. And you again multiply both sides with gamma of 2z. So it's gonna be minus, and it's gonna be here as gamma of 2z. So basically we're talking about, we can just like write this as 2 to the 1 minus 2z times the square root of pi, that's factor, and then gamma of 2z. Hence proved, guys. This was the Legendre duplication formula, and we did this maybe, I'm not sure, oh I'm sorry about that. Okay, sorry. We did in half of that video, which I just provided, I uploaded earlier. I think it's 2 months, I think 2 months ago. So you can check that out if you want. Yeah, again, you should not be checking at the length of the video, but if you are got to learn something, if you got to learn something from that video, so that does matters. If you are learning from that video, because I am just making you to learn from my video, so that is why I'm here. So if you don't just check at the length of the video, maybe I have uploaded a lot of videos, like I just sat straight 2 hours, I think, yeah, it's 2 hours, and I just solved I think more than 30 integrals at once on tablet. So yeah, it's not about the length, but it's all about what you are getting from that video, because you are giving your precious time to this video, so you got to learn something from this video, and if you are learning it, yeah, your time is utilizing, that's it. Okay, it's not a philosophy class, I think. So okay, so now we have some time. Actually, we are very far away from 32 minutes, I think. Okay, so now let's talk about this square root of pi. So I have talked about in 2 videos of this one that which I'm just going to talk about here in a little bit, and maybe I'm just going to bring a lot of videos on this in future. And this is the Euler's reflection formula, and I have proved this I think 2 times. So again, this is really amazing, and you know what, this is going to help us I think everywhere in higher mathematics, but it's gonna help us a lot in gamma and beta functions, a lot. So it's basically it's gamma of z times gamma of 1 minus z equals pi over sine of pi z. So this is what the Euler's reflection formula is all about. And when you plug z equals 1 over 2 here, so this is going to be gamma of 1 over 2, so far it's good. And 1 minus 1 over 2 is also 1 over 2, so times gamma of 1 over 2 even. And when you plug here, so it's going to be sine of pi times 1 over 2, which is sine of pi over 2, and that is 1. So basically we are having pi here. So these two things are identical and being multiplied to each other, so basically they are squared. So that is gamma of the square root of 1 over 2 is pi, and hence we can say that gamma of 1 over 2 is the square root of pi, taking the square root both sides from here. So yeah, I did prove this in one of my videos, I'm not sure which one, but yeah, I did that. And we don't need to take another video to prove this down. The condition is you have to know about this thing, the Euler's reflection formula. Yeah, okay. And you know what, let me just spark a curiosity in you after this thing that I'm just going to talk about here. Let me just talk about that. Just wait a little bit. So I think I'm just gonna bring my next video, or maybe next to next video, because maybe I'm just gonna come up with the triplication formula in the next video. But after triplication formulas video, this is going to be amazing. Let me just tell you what is that. I think actually it is this one, because that's really important. And you know what, we can talk about gamma of, we are here and we have talked about gamma of 2z, and in the next video we are going to talk about the gamma of 3z. But what about if we talk about the gamma of nz? Did you got something goosebumps here? And that is what our Gauss was. So Gauss formulated this crazy formula that is saying that the product as k goes from 0 to n minus 1 of gamma of z plus k over n equals 2 pi to the n minus 1 over 2, next n to the 1 over 2 minus, I think it's nz. Oh, let me just check that out. Yeah, and times gamma of nz. That was it is known as Gauss multiplication formula. And what about, I'm just going to prove this down in front of you all. Isn't that amazing? And yeah, it's really, it's a spark of curiosity inside us, because well, from here we can derive the triplication formula even when you just plug n equals 3. You just have to solve a simple looking product from k equals 0 to 2, because 3 minus 1 is 2. So you can just solve this down and you just have to plug here 2. So it's literally very easy to prove that down. But we're not going to use this one. We can easily use for n equals 5, n equals 6. But again, we are here to learn, not choose the easy path actually. to just make our life easier? Well, we can use some different and long approaches if you are getting to learn something from that approach. But still, yeah, in sense spark. It's a spark in you guys of curiosity. And again, yeah, in this video we have proved this formula, right? So it's a homework for you guys. You just have to plug n equals 2 here and just talk about that, and tell me in the comment section that you are getting this result or not. Obviously you are gonna have, because it's not being proven by me. It's proven by Gauss. I think it's the he is known as the prince of mathematicians, I think. Yeah. So yeah, it's fine, and I think it's good. And I would just request you to just come up in the next video, because we are just going to talk about the duplication formula, and then we're going to talk about the implication formula. I'm not sure. Yeah, that's not cool. But we are just going to talk about the n. Like n could be anything. So yeah, that was my motive here. But still, if you want to look at what would looks like the triplication formula, so you just have to plug here n equals 3, and you're gonna have that formula. But I will not leave you guys at this. I'm just gonna prove this relation down in front of you all. Don't worry about that. Okay, so for now I think it's fine. And yeah, thank you so much for watching this video, guys. If you got to learn something from this video, please make sure to like, subscribe, and please comment down if you got to learn something, or I'm sorry, if you got any kind of doubt in this proof. So yeah, I think we should just cut off right now and stay tuned for the next video, guys, because some videos are gonna blow your mind. It's going to be a crazy journey in beta and gamma functions journey. Thank you so much, guys. Goodbye.